All right, welcome to a lesson on probability. Today we are doing a bit of a review. We're going to talk about tree diagrams, how to use fractions to establish probability. And for most of you, this will be a quick review just to make sure that you're still on top of this stuff. Particularly, tree diagrams are kind of a love-hate relationship. It's kind of like number lines. If you get them, you've got the concept really well, but some people definitely are not a fan. How many of you are like, yeah, tree diagrams make it pretty simple to understand? How many of you are like, gosh darn, those tree diagrams? Yeah, exactly. So we'll take another stab at it and see where you are with it, and then we'll send you off to do your assignment. First, something also that's come up in our MRLCs, I just want to point this one out before we go on. Remember that when you have something beside it, there's that transitive property where it multiplies each thing inside of it. I just thought I'd mention it since it's coming up. I know when I was marking MRLC that came up a few times. First it says, working with a partner. Now we're not going to do this, we're just going to represent it really quick because we have covered probability in the past. A probability experiment involves tossing a coin, rolling a die labeled 1 to 6, and spinning the pointer on a spinner with 3 congruent sectors, or congruent meaning side by side, colored pink, purple, and yellow. Use a tree diagram or a table to find the probability of each event. So the first one is, what are the odds of tossing a heads, rolling a 2, and then landing on purple? Now it says to use a tree diagram, but first let's go for the symbolic and then we'll go to the visual. So if I have a coin and the die and then the spinner, what are the odds? Let's see, it says tossing a heads. How can I represent that as a fraction? Yes, sir. 1 out of 2 or 1/2. So like so generally speaking, if I flip it twice, one of them will probably be a heads. And is this our theoretical or experimental probability? Theoretical. So in theory, we have a 1 in 2 chance of getting heads when we flip a coin. But experimental could be different. Could I flip a coin twice and get tails twice?
Yes.
I could, okay. What are the odds that I roll a 2 on that die? Yes, 1 out of 6. So theoretically, our theoretical, I don't know if that's on camera or not, our theoretical probability is that 1 out of 6 times we will roll a 2. And the spinner, I'll just jump in with this one, that's 1 out of 3 times. Now, if I were to do this symbolically, it's pretty darn simple, but we're going to get into the tree diagram first. I'm going to start your tree diagram, and then I'm going to pause the video and give you a shot at doing the rest of this tree diagram. So first, I'm flipping a coin. So I have a chance of 1 in 2. Okay. So here's the coin. This is the coin part. And I could get a heads or a tails. You with me so far? Okay. Now I'm going to roll the dice, and I have a 1 in 6 chance. So let's say I rolled that heads. Now I've got a 1 in 6 chance. And if I roll the tails, I also have a 1 in 6 chance. So this would be a 1, 2, 3, 4, 5, or 6. Start with that and see if you can finish this off with the spinner. All right, ladies and gentlemen, most of you are showing me rather well that you've got those tree diagrams. I'm very proud of you, by the way, because that was months ago that we did this, so I'm really excited to see that you've retained. So, 7 square. So we've got a 1 in 2 heads or tails. But from each of those, we now spawn 6 off of each of those because we have a 1 in 6 for all the die. And then from each of those branches, we now have 1 in 3 of the spinner. But what we need to first do is answer the question now. Tossing heads, okay, tossing a heads. So now we're on this path. Rolling a 2, now we're on this path. And then landing on a purple. So it looks like one time I could get that out of how many possible outcomes. Now, possible outcomes, what I mean is I could get heads, a 1 and a pink, or a heads, a 1 and a purple, or a heads and a 1 and a yellow, or a heads and a 2 and a pink, and a heads and a 2 and a purple, or a heads and a 2 and a yellow. Do I need to do all of these?
Yep.
No, I'm not doing all of them. Okay. How many are there? Well, let's see. 3, 6, 9, 18, 27, 36 outcomes. So that means 1 out of 36. Well, wait a minute. 1 times 1 times 1 equals.
1.
Oh, good. Man, did we ever have to go back far if you didn't know that?
3.
Alright, and 2 times 6 is 12 times 3. Bing, bing, bing. We good? Alright. Now feel free to take that sound and make it a notification on your phone. Emulation is the highest form of flattery. I'm just kidding, it'll make you look really dumb, even worse than what I just did. So don't do that.
I think we understand.
Alright, let's take a look at a couple more quick examples. There's your tree diagram. I'm not going to labor this one. I'm just going to say, there it is. If you want another example, if you're asked to do a tree diagram during your lesson, you're like, what? But most of you seem to get it. Then I would come back here and I would take a look at this example for another example of tree diagrams. This is where it goes into probability, where all we're doing is using the symbolic, where we've got a chance of 1 in 3, 1 in 3, 1 in 3. That's like what we did up top here. So I'm not going to labor that because we already did an example. And then here you have even more examples of this. But now we're getting into percentage and we're starting to use decimals. And that's something that is a little more unique that we have not done. So if you're watching this video right now to get a review, definitely open up to this page and take a look. I'm going to zero in on the page a little bit. You probably can't see it because we don't shoot these in Ultra HD 8K OLED 3D, whatever, Samsung Schmookfest. So if you don't have this textbook, probably you have access to the class blog and you can download the PDF, or you can run and get one from the class, or you can steal one online if you're a cyber criminal of your choice. I did not promote that, I was just making a joke. So it says, these events are independent, and one word you're going to find a lot in this assignment is independent events. So for example, we talked about doing our coin toss. The odds of a coin toss are independent. If I toss a coin and I get a heads, am I guaranteed to get a tails next time?
No.
No, it's independent. Every time is an independent event that does not rely on previous events. So this says, day in July, 20% probability rain in Vancouver, 65% probability rain in Calgary, 75% probability in Saskatoon. What's the probability it will rain in all 3 cities on that day? So what they did, they took these percentages and they're turning them into decimals. Let's take a look at our board. I'm going to pause, I'm going to start you off, and then we're going to do some show me board. All right. I was really excited by one of your boards. One of you did something I did not expect in the least. Now, first, I did notice one person was trying to do a box model to compare 2 independent events, which we did in 7.5. However, that won't work because we have 3 independent events. So we would have to do a 3-dimensional cube model at that point. But I noticed someone right away changed these 2 fractions. I thought that was a really cool idea. So let's take a look at that and then we'll get to our decimals. So I got 1 times 13 is 13. Times 3, I believe, would be 30 times. And we have 5 times 20 is 100, times 4 is 400. So this person found a fraction that 39 out of 400 days, with this probability, it would rain in all 3 places. But we were looking for a percentage chance, and we'll get back to this. Now most of you you took that 20% and you changed it to a decimal, changed to a decimal, changed to a decimal. And when you multiplied them all together, because when we do independent events, we multiply them together, you got, was it decimal 0975? Was that make sense? So maybe 975 times, or out of 10,000 would get me there. Now take your calculator, take 39 divided by 400. Do you know where I'm going with this?
It's the same.
You think it's gonna be the same?
Wait, actually,
It's
then
the same, it should be the same. And so, first, I gotta say, hats off to,
Joe.
Frederick here. Hats off, Frederick. That was pretty cool. And if you wanted to do it that way, you could. And you could simply do this and turn it into a percentage. Now, when we have this as a percentage though, now we've got to convert it. Percentages always end at the hundredths. Tenths, hundredths. I could call this 9.75% chance that it would rain in Vancouver, Calgary, and Saskatoon on that given day, given those averages. Of course, is the weatherman always right?
Yes.
No, perhaps we should upgrade that to weather person or weather specialist, I should say. So now you've got all the examples. We've got percentage of probabilities. This is where the same person was converting them into fractions or decimals to put them together. And so that's what Frederick showed us right there. So well done, Mr. Frederick. And I think you've got everything that you need for this lesson. Your numbers, I think, are 4 to 14, but you might want to check on the blog to double check. And I would love to hang out and talk about these at the U-shaped table to help you out.